Okay. And good evening. Good for someone. Good morning. I'm Yuichi Tsuda, and thank you for the good introduction, Maeda-san. So I'm very great honored to give a talk here, and thank you very much for giving me the opportunity. And I hope all of the participants are well under this worldwide COVID-19 pandemic. So can you see my screen now?
We can, yes.
Okay, then let me start. So today's my talk is entitled Road to Hayabusa2 from CanSat and CubeSat. And I would like to share with you my experience and my view based on 20 years of my experience in Japanese space engineering. And as I wrote here, I am the first generation CanSat and the CubeSat guy, and my career began with CanSat, as Nakasuka-sensei said. So I'm so grateful to show as one of the example of the space engineering career and what can happen as the result of CanSat education to today's participants. Okay. Okay. So let me first briefly introduce myself. I'm Yuichi Tsuda, and currently I am a professor in ISAS, JAXA. And the ISAS is a Japanese Institute for Space Science. And my research field is the innovative space system, solar system exploration, and astrodynamics. And my experience started from CanSat and then CubeSat development as a student. And after that, I joined ISAS as an assistant professor and then participated in several deep space missions like IKAROS and the Hayabusa2 as a deputy project manager and project manager. And I was in, okay, next one. Oh, okay, then let me start from the beginning of my career. So most of part, actually, Nakasuka-sensei already told, the story started from 1998 when I was a student in Professor Nakasuka's lab. And he gonna get, one day, Professor and I and some other students had a lunch in the university cafeteria. When he asked us, there will be a workshop in Hawaii. Do you want to go? And my answer is, wow, Hawaii, I will go. By the way, what will we do there? And actually, even professor does not exactly know what would happen in this workshop. And the name of the workshop was a University Space System Symposium. And the workshop is the place the story began. And in a sense, the charm of Hawaii was the primary contributor to the beginning of the CanSat program, I think. Then, so my first lesson learned is luck is important. And this chart the Nakasuka-sensei already showed. I traveled to the Oahu Island of Hawaii with Nakasuka-sensei and a few other students in my lab in the summer of 1998. And there we met Professor Bob Twiggs of, at that time, the Stanford University. And yeah, so I'm also so honored to have him in this meeting. So in the workshop, he passionately proposed like, yeah, let's make a satellite out of this coke. And I didn't understand what he said. We could not believe we, just a student or just a small lab, can make a real satellite and launch it to space. But it sounds super exciting. And the way Twiggs sensei told sounded real and practical. So after doing small internal lab meeting on site, then we decided to take part in his proposal. And we did not know the way, but we were excited a lot from this idea. And the first concept he proposed was like this, and we would see in the next USSS next year, and did some operation, space operation by the CanSat. So that's the first initial concept. And the research field of my lab at that time was space engineering, so we already knew something about space engineering, but we knew little about how to use our hands to make something for the spacecraft components. So the first thing we did was to go to Akihabara, which is a city with full of electronic shop in Japan, and bought CPUs, condensers, resistors, and some other electronic mix at the electronics shop, and made a printed circuit board PCB by photoresist by ourselves, and so on. And the another thing we did was to buy as many juice cans as possible for structure design and experiments. And you can see very primitive handmade circuit board with bad soldering. But anyway, we started making a CanSat. And in the meantime, I think Professor Twiggs realized it was difficult to launch the satellite into space in just 1 year. And he proposed an alternative option by collaborating with amateur rocket people based in Black Rock Desert in the United States. Let's do the suborbital experiment. That was his new proposal. And finally, we completed the fabrication, and we made 3 CanSats like this. And I made the number 2 CanSats. And in the summer of 1999, we brought these 3 CanSats that we made to Black Rock Desert. And everything was new to us. And actually, everything was new to everyone, because this was the first time first CanSat event. And our CanSat was loaded to a rocket provided by a medical doctor. It was a very beautiful rocket. The launch was successful, and 2 CanSats were successful, but only one, my CanSat, failed. And after the separation from the rocket, the parachute was deployed successfully, but I could not receive any signal from my CanSat. The reason was very clear. I changed the transmit antenna just before the launch because it better fit to the rocket. And I thought it had better performance. But in reality, we only had tested it with the old antenna before coming from Japan. So I learned very important lessons learned from here. So like test as you fly as you test. I think all you already know, well, this is an essential rule for the space engineering. But for me, I learned this through the real bad experience. And fortunately, I put the memory in my CanSat, and all of the flight data could be retrieved later. So another lessons learned here was prepare backup. And we continued CanSat activities after the first Black Rock event, but at the same time, we strongly felt we want to make a real satellite. And in the next year's workshop, again in Hawaii, Professor Twiggs proposed another idea. Let's make a 10-centimeter cubic satellite. We thought this is a great idea because through the 1-year experience of developing CanSat, we found it very difficult to accommodate many functions to cylindrical CAN. So you know, IC chips are all square shapes, and it's easier to make square PCBs than round PCB. So we started to plan what mission we have to do with the CubeSat, and decided to combine with our lab research activity. At that time, we were interested in ultra-light structure application in space. And this is one of the such example I made, the Pluto Explorer concept. It is equipped with about 200-meter diameter huge membrane attached with solar cells so that the spacecraft can be driven only with the solar power in the Pluto distance. And we thought to apply this concept to the CubeSat like this. And then after studying the feasibility again and again, finally the design resulted in CubeSat without membrane like this. And we realized we have to begin with very basic of the satellite to obtain fundamental know-how of the satellite fabrication. So we decided to keep it very, very simple. And after we succeeded then we will be able to think about more sophisticated space applications like space membrane. So the first CubeSat is only equipped with the camera to take a picture of the Earth. Let me skip this. So then in 2020, sorry. Yeah, okay. Then in 2022, we completed the CubeSat named Sci4. And you can see camera here, and behind it, you see the power board, communication board, and so on. And finally, we could make a beautiful CubeSat. And our CubeSat was actually launched by Russian rocket, and the launch was successful. I cannot forget the moment the first signal was received in our ground station. It was a beautiful Morse code tone signal. And after then, CubeSat sent us a beautiful Earth scenery regularly. Surprisingly, this CubeSat is still alive. So it is alive for 17 years in orbit, still sending Earth images to us. So my pride is that our CubeSat lives longer than most of JAXA's and the NASA satellites.
Was this the first 1U?
Yes, this is the first 1U.
By the way, you have 10 minutes left.
Okay. Then from I will speed up. From 2003, I joined ISAS, and there I continued my research on membrane. And in ISAS, there was a study group on solar cell, which wanted my idea of the space membrane technology. And then I applied my research result to the concept of a solar cell in JAXA. And finally, we made it. After we did several experiments, we proposed an interplanetary solar cell mission in 2007 to JAXA, and was authorized to launch in 2010. It is a 300-kilogram small spacecraft, and you can see a membrane here, which is a solar cell surrounding around the spacecraft body. And it was launched in May 2010 and flew to Venus. This is a real picture of the flying IKAROS. We confirmed that the spacecraft was actually propelled by the solar radiation pressure and could control it to change the orbit. And this is the mission scenario of IKAROS. IKAROS made a Venus flyby 6 months later, and extensive in-orbit solar cell experiments were conducted in these 6 months, and some extended mission after them. And that was so successful mission. And then my interest directed strongly toward deep space exploration. And I was lucky enough to join the Hayabusa2 project from its beginning. You may know it successfully completed the round-trip mission to an asteroid recently, and let me use the rest of my presentation time to introduce Hayabusa2 result. So this is the Hayabusa2 mission scenario. It's a sample return mission to a C-type, a carbon-rich asteroid named Ryugu. It was launched on December 3rd, 2014, and after 3.5 years of interplanetary cruise, it arrived at the Ryugu in June 2018. And the spacecraft stayed for 1.5 years in the proximity of the asteroid Ryugu and attempted many challenging missions like deploying multiple rovers, 2 touchdown and sample collections, and the kinetic impact to create the artificial crater, and the asteroid orbiting by multiple objects, and then return back to the Earth just 1 month ago, December 6, 2020. And I was the project engineer, which is the lead of the spacecraft design in the development phase. And now, after the launch, and currently I am the project manager of the Hayabusa2, which is the leader of the whole team. And Hayabusa2 looks like this. It's just a 600 kilogram, relatively small spacecraft compared to other interplanetary missions. But it's a round-trip space capable spacecraft. And this is a Ryugu, and the shape of Ryugu, appearance of Ryugu was only acquired after the spacecraft actually arrived there in 2018. The shape was surprised us. It's a top shape with a very circular equatorial bulge, and the size is just smaller than the 1 kilometer, and it rotates about 7.6 hours. It's about 3 times faster than the Earth. And what was the most headache for us is that the terrain is covered by the rocks all over the globe. So it's very bumpy asteroids, which made us difficult to land on the surface of the asteroid. But anyway, we started from the easier one. They're deploying the multiple rovers to the surface of the asteroid. 3 rovers from Japanese university and also the space agency, and also one international lander from D11 CUNES, our international partners, and all of them are successful. And then, although we found that it's very difficult to find a safe place to land, we actually improved our landing software and upload that, and then adjust to the terrain of the Ryugu. And after 4 months delay, we decided to perform the touchdown operation in February 2019. And the sequence that looks like this. So first we dropped the target marker, which is a visual navigation marker, navigation landmark. And by using that, spacecraft could automatically land to the safe place in the vicinity of the target marker like this. And the sample collection is actually very short. It's a touch and go sequence. And once the touchdown is detected, the projectile is ejected from the root of the sampler horn. And the sample is collected like this. And the actual movie, we got the actual movie like this. So you can see that the spacecraft stably descending to the ground. And then you can see a lot of ejecta as a reaction of the projectile ejection. And actually this time the landing accuracy was only 1 meter. It happened 300 million kilometers away. So it's a surprisingly satisfactory result. And after that, we did very different, another new missions, doing a kinetic impact mission 1.5 months later, after the first touchdown. So this is a kinetic impact device, and it will explode soon. But before that, spacecraft has to escape to avoid the debris from the explosion. And where to escape? It should go behind the asteroid. It's the only place, the safe place to escape. And then explode and make a hole like this. And then the spacecraft itself could not observe the crater forming process. So we deploy actually CanSat called DCAM3, which is a CanSat Cork can size remote camera, which is to observe the crater forming process in the staying in a dangerous zone like this. So it's a very challenging mission, but we actually perfectly succeeded in this mission. You can see a beautiful crater forming movie like this. and we could see a very large reaction of the kinetic impact. And the crater we made sizes about 14.5 meter diameter and a depth of about 3 meters. So that's a very big hole. And after that, what we want to do is to land in the proximity, in the vicinity of the crater to collect the subsurface material. It's a fresh soil of the cosmic soil. So the second touchdown was conducted 3 months later in June, and that was also successful. And that time, the landing accuracy was only 60 centimeters, which was far more better than the first touchdown. Then, then finally, after we left the Ryugu, 1 year of another return cruise, then the spacecraft returned to the Earth last month. And I will show you this short movie about the reentry and the recovery operation. Please watch this. Okay, then actually we got plenty of Ryugu sample like this. So we have 3 chambers in the reentry capsule, and the first chamber we have a first touch sample from the first touchdown, and in the third chamber we found the sample from the second touchdown. So and the total yield is 5.5 grams, which is far more than the design criteria requirement of 0.1 gram. And the spacecraft itself is still flying. So after the reentry, the spacecraft escaped from the divert from the Earth's reentry trajectory and continue the interplanetary flight. And the 6 years later, we will fly by another asteroid 2001 CC21. And then after 2 Earth swing by, hopefully we will arrive at the second new asteroid called 1998 KY26. It's another rendezvous. So the journey is still continuing. So this is the last slide. So to me, the CanSat was the first step to my career, and I got many lifelong friends in CanSat and CubeSat activities. And some of them played a critical role also in the Hayabusa2 project together with me. Some of them are in this photo. So I really appreciate CanSat CubeSat activity, and they gave us many good friends and precious experience. I hope the world of the small sats more and more contribute to the space missions in a direct and indirect manner. So thank you for your attention.